In this lesson, we will study how to measure angles in radians, and we'll begin by defining what we mean by 1 radian. We say an angle that has its vertex at the center of a circle and that intersects an arc on the circle equal in length to the radius of the circle has a measure of 1 radian. And you can see here we have theta, and theta represents this angle right here. And when we talk about the intercepted arc, here's the initial side and the terminal side, and this represents the intercepted arc. And we're saying that it measures whatever the radius measures. Here's our radius, and this length is the same as that length, and that's why we say that theta is equal to 1 radian. In order to find the number of radians that theta equals, we always take the length of this arc and divide it by the length of the radius. Now, I'd like for you to see something. Here I have an angle theta in standard position. There's the initial side and there's the terminal side, and I'll go ahead and label this theta. And I wanted you to see, once again, this theta is 1 radian, but I wanted you to see that it didn't matter what size the circle was, that it didn't change the size of the angle. That if we look at the smaller circle, this arc is equal to this distance, which would be the radius of the smaller circle. For that middle-sized circle, this distance would represent the radius, and this intercepted arc is equal to the length of this radius. And look at the larger circle. Here's your radius for that larger circle, and can you see that the arc that the angle intercepts is the same length as the radius? So we would say that this theta measures 1 radian, and it doesn't matter whether it's a small circle or whether it's a large circle. And what 1 radian is really just this. We call this arc length S divided by the radius. And we're just dividing R into S. And we don't have a symbol for radians. So if you see that theta is equal to 3, if there is no degree symbol there, then you are to assume that that means 3 radians. And of course what that would mean is that if you found the arc length and divided it by the length of the radius, it would go 3 times. Consequently, this is just a number. And for higher math, usually we are interested in angles that are measured in radians, that represent the number of times that the radius divides into the arc length, instead of having them in degrees. Now, I sort of wanted you to have an idea of the size of different angles measured in radians, and so really we can ignore some of this. And we've already talked about when theta is equal to 1 radian, and see, here would be my initial side, and there's my terminal side, and this arc length is equal to 1 radius. Now, what if theta was equal to 2 radians? Well, that would mean that the intercepted arc divided by the radius would equal to 2. And here is a theta this theta is equal to 2 radians. And I don't know if you can sort of see, you see this arc length, that intercepted arc? The arc that goes between the initial side and the terminal side. Does it look like it's about twice this radius? It is. Well, now let's look at 3 radians. So there's an arc length that's the length of 1 radius, 2 radii, the second radius, and then the third one. Let's see if you can see this angle. Okay, so here's my initial side, and now I want you to look at the angle that goes all the way over here. That would be 1 radius, there would be your second, there would be your third. Does it look like that? That's 3 of this distance? And so all the way over here would represent the terminal side of theta that was equal to 3 radians. And then if we move on to 4 radians, 1, 2, 3, 4. So this arc length from this initial side to this terminal side would be 4 times this radius. And then 5 radians. I think they'll have to take that off. If I go all the way around to here, 1 radius, 2, 3, 4, 5. Can you see that the arc length from here to here would be equal to 5 of the radius? And so we'll call this angle with the terminal side here as 5 radians, and all the way to here would be 6 radians, because if you took the arc length and divided it by this radius, it would go 6 times. So it's very important that you realize that to find theta, you find the length of the arc and you divide it by the length of the radius, and consequently you get that theta is equal to a number. It is the number of times that you can divide the arc length by the radius. Now what I would like for us to do is to relate radians to degrees. And let's just look at a circle. All right. Now, we know what the arc length is for the circle when we talk about the circle's circumference. Circumference is the whole distance around. So let's pretend like this is my initial side. All the way around would be my terminal side. What does this angle measure in radians? Well, we know that to find that angle theta in radians, we need this arc length, which would be S. And do we know what this arc length all the way around is? Well, yes, that's the circumference of this circle. And we know that the circumference of this circle is 2 times pi times r, don't we? So the measure of this arc length is 2 times pi times r. If we divide that by r, what do we get? We get that the central angle for the whole circle measures 2 pi radians. Now, what do we know that the measure of this central angle is in degrees. We know that it is 360 degrees, don't we? So 360 degrees is the same as 2 pi radians. Now, first thing we're going to do is to divide both of these by 2. And 360 divided by 2 gives us 180. And 2 pi divided by 2 gives us pi radians. All right, that's the fact that we're going to need to know to convert angles measured in degrees to radians and to convert angles measured in radians to degrees. So let's look at this and make sure that you get it written down. 180 degrees equals pi radians. All right, so when we get ready to use this, when we convert degrees to radians, we will multiply by pi radians over 180 degrees, and to convert radians to degrees, we'll multiply by 180 degrees over pi radians. So make a note of that. All right, I'd like for us to look at some problems. Usually you'll have two different types of problems where you convert degrees to radians. The first types will say to convert the degree measure to radians, but to leave your answers as multiples of pi. And usually the things that you convert are your special angles. So you can see I've got 45 degrees here, and so I'll use the dimensional analysis conversion factor if I want to convert degrees to radians, and I know that 180 degrees equals pi radians. Then I multiply by a unit fraction where I want to put the pi radians in the numerator and divide by the 180 degrees. That way the degrees cancel, and this is legal because since pi radians equals 180 degrees, this is considered a fraction that is equal to 1, which we call a unit fraction. And so that's what we'll do for both of these problems. Since we're supposed to leave this in terms of pi, we will be able to reduce it. If you need to, you can think of that over 1, but I don't usually, do that. 45 goes evenly into 180 4 times. So we'll say 45 goes into 45 once, and of course those degrees cancel these degrees, and 45 goes into 180 4 times. So we'll get 1 times pi is pi over 1 times 4 is 4. So what we know here is that 45 degrees equals pi over 4 radians. And that's what they mean by leave answers as multiples of pi. You will still have a pi as part of your answer. We'll do the same thing here. And I always tell my students when they're using this unit fraction that whatever you have in the numerator here, and that's like it's over 1, then you want in the denominator over here. So that's how I know the degrees go there. And pi radians in the numerator. And once again, let's see, what divides evenly into 240 into 180? 60. And so 60 will divide into 240 4 times, and 60 will divide into 180 3 times. So we'll have 4 times pi is 4 pi over 3 radians. And so our angle 240 degrees equals 4 pi over 3 radians. And you don't really have to write radians. When you see this, you should recognize that it's radians. Sometimes we would prefer to write it as 4/3 pi. And that's really up to you. I usually write it like this, but you should know it both ways. And right here for pi over 4, you could write that as 1/4 pi. And that would mean the same thing. All right, I want us to look at the second type of problem where we're given an angle measured in degrees and we're supposed to convert it to radians. It says convert each degree measure to radians, and notice it doesn't ask us to leave it as a multiple of pi. Well, that's because neither of these angles is one of our special angles, nor does either one of those have a reference angle equal to our special angles. We work it the same way, we use the same process, but what we have to do is actually calculate it out. We will want to multiply by pi over 180 degrees. And what we will literally do is we'll put this in our calculator, we will multiply it by our pi button, and then we will divide by 180. And remember that for your calculator, it does not want an angle in degrees and minutes. So you've got to take this part and convert it to decimal degrees first, however your calculator does that. And just as a reminder, if you don't know the shortcut on your calculator, then you enter the 165 plus 10 divided by 60, and that's because there are 60 minutes in a degree, and we want to know what part of a degree 10 minutes is, and push your equal. So you would want to do that, then multiply by your pi button. All these scientific calculators have a pi button, and then you want to divide by 180. And it doesn't tell me what to round to. Well, usually for an angle measured in degrees, we round to 4 significant digits. Here's what I get. Now, I've converted, and these were the exact steps. Don't forget to put that equals in there so that it will add and divide for you. And then you want to multiply by pi, and then you want to divide by 180. And the number that I get when I do all of this is 2.882702, and it keeps on going. But we will round to 4 significant digits. So 1, 2, 3, 4. Since this is a 7, since that's larger than 5, we'll add 1 there. So it would be 2.883 radians. And we'll do the very same thing here. We'll multiply by pi over 180, and that's pi radians over 180 degrees. And since this angle is already given to us in decimal degrees, we don't have to worry about the conversion. Those degrees will just cancel each other out, and so you'll just go 94.2 times your pi divided by 180. And let's round to 4 significant digits. And rounded to 4 significant digits, we get 1.644. And once again, I'm writing radians, but if someone was talking about an angle and they just said it measured 1 in 644 thousandths, or they said 1.644, then you should assume it's in radians because they did not say degrees. Now, there are 8 special angles that if someone names them in degrees, you should automatically know what their radian measure is, or if you're given their radian measure, you should automatically know what their measure in degrees is without having to figure it out. So I want us to look at those 8 angles right now. Actually, one of them we already know. We figured as one of our problems. So the first one I'll call to your attention, and of course all of these angles have initial side on the positive x-axis, and the angle that splits the first quadrant here is 45 degrees, and we found that it's equal to pi over 4 radians, didn't we? So I'll go ahead and label that. And then the angle that I want us to look at is the angle whose initial side is on the positive x-axis, and there is no rotation, and so consequently its terminal side is also on the positive x-axis, which of course is 0 degrees. Well, when we convert 0 degrees to radians, we'll say 0 degrees times, we'll use our conversion factor, pi radians over 180 degrees, and of course 0 times pi is 0 over 180, which gives us 0 radians. So 0 degrees equals 0 radians, but we don't have to write the radians, it's understood. The next one that I would like for us to look at is 90 degrees. Of course, initial side positive x, terminal side in this case is positive y. So what happens when we convert 90 degrees to radians? And of course we do it the same way. Well, of course the degrees cancel. 90 goes into 90 once and into 180 twice. We are left with 1 times pi is pi over 2. So 90 degrees can be written as pi over 2. It could also be written as 1/2 pi if you would prefer. Now, I want to carry this one step further. I want us to see what decimal this equals, and we'll do that by just taking pi and dividing it by 2. So use your pi button on your calculator and divide it by 2, and you should get 1.5707, and we'll just say that pi over 2 approximately equals to 1.57. And what I want you to understand about this is, remember what we mean by radians? When we talk about an angle measured in radians, whatever number that angle is, that means if we take this arc length, and we're talking about the arc length intercepted by the initial side of 90 degrees and the terminal side of 90 degrees, this arc length right here, and we divide it by the length of this radius, this radius would divide into that arc length 1.57 times, which we would prefer to use the pi over 2. And that's the number that pi over 2 is approximately equal to. Now, we know for this angle in degrees, this straight angle where the initial side is positive x and terminal side is negative x is 180 degrees, don't we? And we know that that's equal to pi radians, and we know what number pi is approximately equal to. It's 3.14. And of course, when we say it equals pi radians or 3.14 radians, we mean that if we take this arc and divide it by this radius, the number we get is 3.14. Now, let's look at our 270 degree angle. And I want you to notice something. Notice that this is half of pi. Does that make sense? There's your pi, and this is half. In other words, this arc is half the length of that arc, and you can see it, can't you? Okay. Well, let's convert the 270. We'll say 270 times pi over 180, and 90 goes into 270 and 180. 90 goes into 270 3 times. Of course, the degrees are going to cancel. 90 goes into 180 2 times. So we're left with 3 times pi divided by 2. So 270 degrees equals 3 times pi over 2. Or sometimes we say 3 pi over 2, or it would mean the same thing to say 3 halves pi. That would be the same thing. But I want us to get a decimal equivalent for it. So on your calculator, say 3 times pi divided by 2. And let's round to the nearest hundredth is 4.71. So the number that this represents is approximately 4.71. And what that means is that this arc between the initial side of this angle and the terminal side, this arc divided by this radius equals 4.71. Now, the next one I want is all the way around, and we've already done that. All the way around, of course, is 360 degrees, and we know that that's equal to 2 pi radians, and to get the number that it approximately equals, we'll just say 2 times pi. You can say 2 times your pi button is 6.28 radians. And so this arc length all the way around divided by the length of this radius equals 6.28. Now, there are 2 other angles that I've got up here. One of them, of course, is 30 degrees, and this other one is 60 degrees, and we want to convert both of those to radians, and we want to leave them as multiples of pi. So, we'll take the 30 and multiply by pi over 180 degrees. 30 goes into 30 once and into 186 times, and the degrees cancel. So what we get is pi over 6. And if we wanted to, we could find what numbers these equal, but it's not as important as your quadrantal angles, because there are times when you need to know which quadrant the terminal side is in, and so you'll have to know these decimal values. The last one we'll do is 60 degrees. We'll multiply it times pi over 180 degrees, and 60 goes once, and 60 goes into 183 times. So we get pi over 3. Now, I would suggest that you copy that down, that you know all of these, because actually we're going to do more work with this. You're going to find in your trig work that you're going to need to know all your quadrantal angles in radians and your special angles in radians and any angle that has a reference angle of one of your special angles in radians. And so that's what I want us to look at right now. And let's start by labeling what we know. You see all those angles? Well, we need to know them all in radians, and so when we get finished, that's what we will have this completely labeled. Of course, we know that with the initial side on the positive x and terminal side on the positive x with no rotation, that's 0 radians. We know that 90 degrees is pi over 2 radians. That 180 degrees is pi radians, that 270 degrees is 3 pi over 2 radians, that all the way around is 2 pi radians. So 0 radians and 2 pi radians are coterminal, meaning they have the same initial side and the same terminal side, just like 0 degrees and 360 degrees are. Now, notice something. This is pi. This is 2 pi, isn't it? Halfway is 1/2 pi, so you can really count that. 1/2 pi, 2/2 pi reduces to 1 pi, 3/2 pi, 4/2 pi reduces to 2 pi. Now, I tell you that because we're going to use relationships like that with our special angles. Let's go ahead. We know these first quadrant ones. We know that this is pi over 6 radians, that this one is pi over 4 radians, and this one is pi over 3 radians. So what I would like for us to start with is to look at pi over 4 radians and look at the angles that have a reference angle equal to pi over 4. Of course, for pi over 4, this is its reference angle. So, what I've done here is I've made the terminal sides of the pi over 4 and its reference angles really dark. And so hopefully you can see this reference angle, but what we're interested in is what is this angle, and notice that its reference angle would be this angle right here, and it is the same as pi over 4. It is pi over 4. And this angle has a reference angle of pi over 4, and this angle has a reference angle of pi over 4. Now that's important because remember that angles and reference angles have trig functions that have the same absolute value. The only difference is the sign, and that's why it's important to know where the terminal sides of these angles are so that you can figure out what the sign of the trig functions are. So let's look at the pi over 4, and I call it the pi over 4 family, okay? All right. If this is 1/4 pi, and of course this is 2/4 pi, which reduces to pi over 2, what is this going to be? It's going to be 3/4 pi, or 3 pi over 4. And we could figure out what the numerical value of that was, but that would mean that this intercepted arc divided by r would equal to whatever number you get when you multiply 3 times pi and divide by 4. So 1/4, 2/4, 3/4. Of course, 4/4 pi reduces to 1 pi. What would this one be? It would equal 5 pi over 4. And it would have a reference angle of pi over 4. So we've got 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi. This would be 6/4 pi, but of course we know it reduces to 3/2 pi. What would this equal? 7/4 pi. And notice that its reference angle is pi over 4. Can you see that's the same as that, as that, as that? And of course, if we took this arc and divided it by the radius of this circle, it would equal to whatever this number is, 7 times pi divided by 4. And notice 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4. This would be 8/4 pi, but of course we know that that's 2 pi. So there are 4 special angles from 0 to 2 pi that have denominators of 4, and I call them the pi over 4 family. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Notice they split the quadrant, and notice that there's 1 for each quadrant, and you need to know. First quadrant is pi over 4, second quadrant 3 pi over 4, third quadrant 5 pi over 4, fourth quadrant 7 pi over 4. So I want us to go back to our paper that we're going to record all the angles on. I think it's good for you to see them separately. I put these light lines in so that you could see how they relate to pi over 6 and pi over 3. But let's go back and let's label. So we know this is pi over 4. Splitting this second quadrant is 3 pi over 4. Splitting this third quadrant is 5 pi over 4. And splitting the fourth quadrant, we have 7 pi over 4. So write that down. What's important about knowing these radian angles by family is that because they have the same reference angle, their trig functions will have the same absolute value. So that's why it's important to learn them like that. Let's look at the pi over 3 family. Now we know this angle is pi over 3. And of course we mean that its initial side is positive x and there's its terminal side. And we know all the way around here is pi. Does it look like that's about 1/3 of the way? I hope it does, because it is. And the next pi over 3 angle is this angle right here. This is 1/3 pi. This is 2/3 pi, or 2 pi over 3. I want you to notice that for pi over 3, this is the reference angle. For 2 pi over 3, this is the reference angle. They are the same. The other thing that it's important for you to understand is that the arc for 2 pi over 3 divided by the radius of this circle would be equal to whatever the decimal equivalent of 2 times pi over 3 is. So we got 1/3 pi, 2/3 pi. This is 3/3 pi, which of course reduces to 1 pi. And what would this one be? This one would be 4/3 pi, or 4 pi over 3. This would be its reference angle, and of course that's equal to this reference angle and to that. So let's see here. 1/3, 2/3, 3/3, 4/3. this one would equal 5/3 pi, or 5 pi over 3. And of course, its reference angle here is pi over 3. And then going back up to the x-axis, 1/3, 2/3, 3/3, 4/3, 5/3. This would be 6/3 pi, which of course reduces to 2 pi. So you've got 4 angles in the pi over 3 family. Notice once again you've got 1 per quadrant. Notice that the special pi over 3 angles are closer to the y-axis in each quadrant. That's the closest special angle to y. That's the closest special angle to y. Down here, 4/3 is the closest special angle to the y-axis, and 5/3 is the closest special angle to the y-axis. So that's the pi over 3 family. Let's label our circle where we're labeling everything. So pi over 3, this special angle that's closest to the y is 2 pi over 3. In the third quadrant, this special angle that's closest to the y is 4 pi over 3. And in the fourth quadrant, the special angle that's closest to the y-axis is 5 pi over 3. So 1/3, 2/3, 3/3, 4/3, 5/3, 6/3. So maybe you can see how that all fits together by thinking about those fractions. So that gets our pi over 3 family. And write that down. We have one more special family to look at, and that's our pi over 6 family. So let's look at it. We know that this angle right here in radians is pi over 6. Now, of course, we're assuming that the initial side is on positive x-axis, and there's the terminal side. And of course, its reference angle is this angle right here, which measures pi over 6. Now, we know all the way to here is pi. So if this angle is pi over 6, that means it's 1/6 of pi. And so what I want you to see is how to count by 6 until we get to pi. And this is 1/6. That would be 2/6 pi. But how does 2/6 reduce? 1/3. And so that's our pi over 3, isn't it? So 1/6 pi, 2/6 pi. This would be 3/6 pi. But how does 3/6 pi reduce? It reduces to 1/2 pi. So that's what we call that angle. So 1/6 pi, 2/6 pi, 3/6 pi. This is 4/6 pi. But how does 4/6 pi reduce? It reduces to 2/3 pi. So that's what we call that angle. So let's go 1/6 pi, 2/6 pi, 3/6 pi, 4/6 pi. What would this one be? It is 5/6 pi, or 5 pi over 6. And it is the only second quadrant angle that's in the pi over 6 family. It's the only second quadrant angle that has a reference angle of pi over 6. And hopefully you can see that those are equal. The other thing, of course, initial side positive x, terminal side here, we know that the length of this intercepted arc divided by the length of this radius would equal to whatever this number is when you say 5 times pi divided by 6. All right, let's continue on to the third quadrant. We've got 1/6 pi, 2/6 pi, 3/6 pi, 4/6 pi, 5/6 pi, 6/6 pi would just be 1 pi, and this would be 7/6 pi, or 7 pi over 6. Notice this is its reference angle, and it is equal to pi over 6. and this is the only third quadrant angle that has a reference angle of pi over 6. So let's go for the fourth quadrant angle. 1 6 pi, 2 6 pi, 3 6 pi, 4 6 pi, 5 6 pi, 6 6 pi, 7 6 pi, 8 6 pi reduces to 4 pi over 3. 9 6 pi reduces to 3 pi over 2. 10 6 pi reduces to 5 pi over 3. And this last one is 11 6 pi or 11 pi over 6. It is the fourth quadrant angle with a reference angle of pi over 6. Of course, we could finish on up here. 12 6 pi would be 2 pi. So these are your 4 pi over 6 family members between 0 and 2 pi. You should learn what they are in each quadrant and where they are in each quadrant, and notice that they are the special angles that are closest to your x-axis. This is the closest special angle to your positive x-axis in the first quadrant. In the second quadrant, this is the closest special angle to your negative x-axis. In the third quadrant, 7 pi over 6 is the closest special angle to the negative x-axis. And in the fourth quadrant, 11 pi over 6 is the closest special angle to your positive x-axis. So let's write those on our sheet that has all of these, and we will be finished with special angles and where they are. Pi over 6, in the second quadrant, the angle is 5 pi over 6. The third quadrant angle that has a reference angle of pi over 6 is 7 pi over 6. And in the fourth quadrant, our angle is 11 pi over 6. So you need to learn where these are, you need to learn what they are, and you need to understand what their reference angles are, because we will be using that fairly soon in our trig work. All right, we've spent a lot of time converting angles measured in degrees to radians and just talking about angles that in radian measure, which is a little different because we're used to angles in degrees. But now what I'd like for us to do is to take some angles that are measured in radians and let's convert those to degrees. There are times when you want to do that. So let's look at those problems. We'll start out with angles in radians that have pi, and notice it doesn't say that it's radians, but when you know it's an angle and it says it's 13 pi over 4, you should know that it's in radians. And to convert it to degrees, now since we'll think our radians are in the numerator, we want our radians in the denominator, so we'll use our unit fraction that relates degrees and radians, and remember that is 180 degrees equals pi radians, but this time, since our radians are in the numerator, we want them in the denominator, which means that we want our 180 degrees in the numerator. And remember, we can do this because if 180 degrees equals pi radians, when we take something and divide it by itself, it is a fraction that's equal to 1. And when you multiply anything by 1, it looks different, but the quantity's the same. Well, what we do here is we can divide those pi's out. They divide to 1. And really, radians don't cancel radians because it's not a true measurement. It's just a number. But if it makes you feel better to feel like that they do, you can go ahead and sort of think it that way. What we're left to do is to say 13 times 180 divided by 4. and we get 585 degrees. So if we have an angle that measures in radians, 13 pi over 4, it is equivalent to 585 degrees. In problem number 6, we'll convert exactly the same way. We'll use our unit fraction that's equal to 1, and we'll use 180 degrees over pi radians. Once again, of course, what happens is the pi's cancel, and even on this one, you could go ahead and say 20 divides into 180. 20 goes into 20 once and into 189 times, doesn't it? I'm not trying to cancel the degrees. The degrees don't cancel out. That was just a slip. But we need to say 11 times 9, which is 99, and so that would be 99 degrees. So 11 pi over 20 converts to 99 degrees. Now let's look at two last problems that give us angles in radian measure, but in a different form. It says convert each radian measure to degrees. Write answers to nearest minute. Well, remember, just plain old numbers like that can be radian measure. If I say the angle measures 4, that means 4 radians. And if you remember at the beginning of the lesson, we actually showed where the terminal side of 4 radians would be for an angle in standard position. But when you're given the decimals like this, you just do the same thing. That's understood to be 4 radians. So you're going to multiply by 180 degrees over pi. And you can put radians, but remember, it's not necessary to write radians. And what you'll have to do here is just completely calculate it. On your calculator, you will say 4 times 180 divided by pi, and of course use your pi button to divide by pi. And it tells me to write the answer to the nearest minute. Well, let me write what I've got. This is what my calculator gives me first, which of course that's decimal degrees, and it says nearest minute. Well, I know that even when I do it to the nearest minute, that the whole number degrees stay the same, so it's going to be 229 degrees. And remember what I need to do to this decimal part to convert it to minutes? I need to take the decimal part and multiply it by 60. And what I do to keep it more accurate in my calculator, I just subtract the 229 off, which leaves me with the decimal part, and then I multiply that decimal part times 60. So I've got this in my calculator. I subtract 229. I'm left with the decimal, multiply times 60. And I get 10.987, and it just keeps on going. Well, to the nearest minute means that I need to look at the 9. Of course, that's 10 minutes. That would be the 1 minute. Since it is a 9, I know I add 1. So it would be 11 minutes. I will work problem 8 exactly the same way. If I have an angle that measures 3 725 radians, then I multiply by 180 degrees divided by pi radians. And once again, I just multiply it out, and once again, my calculator will give me my angle in decimal degrees. So let's do this. Let's go 3.725 times 180 divided by pi, and hit your equals. And here's what I get. And once again, I need to convert the decimal part of this to minutes, but of course the whole number part will just be 213 degrees. And most of your calculators have a shortcut way to do this, so feel free to use the shortcut way, but if you don't have the shortcut way, then you just need to multiply this decimal part, decimal 4267787, times 60, because there are 60 minutes in 1 degree, and we want to know how many minutes this part of 1 degree is. I still say it's the easiest. Subtract 213 if you don't know the shortcut, and press your equals, and that leaves you with the decimal part, and just multiply it by 60. And so here's what I get, and since it's to the nearest minute, all I really need is to the nearest tenths place, and 6 cents in the tenths place, that's a 6. I'll add 1, and that'll give me 26 minutes. So this angle in radians is equal to 213 degrees, 26 minutes. That completes the radian angle measure lesson. It's very important that you understand that to find the measure of an angle in radians, you take the intercepted arc S and divide it by the radius. It's also important that you are able to take any angle in degrees, and you know to multiply it by pi over 180 to convert it to radians. Any angle in radians, multiply it by 180 over pi to convert it to degrees. And for your special angles, you should know what they are in radian and degree measure without having to convert. You should just know that, and you certainly should know all of your special radian angles from 0 to 2 pi. So take some time to memorize those, and it'll make life in trig a lot easier. Please rewind the tape if you're finished with it. Thank you.